Alright, thanks for watching. And today I would like to talk to you about an extremely beautiful concept in linear algebra called simultaneous diagonalization. In other words, how can you turn two matrices into a diagonal matrix at the same time? So let me just recall the definition of a matrix being diagonalizable. So A is diagonalizable if and only if you can write A as PDP inverse for P invertible and D diagonal. Now, what would it mean for two matrices to be diagonalizable? So if A is diagonalizable, then this means that A is PDP inverse, right? If B is diagonalizable, it technically means B equals to some other matrix, Q, some diagonal matrix, D prime, and Q inverse. Well, if A and B are simultaneously diagonalizable, then it turns out you can use the same P to transform A and B into diagonal matrices. So simultaneous diagonalizable means if A is PDP inverse, then B is also PD prime P inverse. So here's the correct definition. A and B are simultaneously diagonalizable so in other words, we don't want to do twice as much work. We just want to choose the same P that transforms both A and B into diagonal matrices. If there exists P invertible such that, well, notice we can actually solve for D. D is P inverse AP, and D prime, it's P inverse BP. So P inverse AP and P inverse BP are diagonal. And careful, not necessarily the same diagonal matrix, because otherwise I think A would be B, but two possibly different diagonal matrices. And also, what does that mean in terms of eigenvalues and eigenvectors? What this means, remember P is really the matrix of eigenvectors. So what this means, you can find a common basis of eigenvectors that turns both A and B simultaneously into a diagonal matrix. Now, that sounds like a very hard job, but it turns out it's not that hard, because here's one of the most amazing theorems in linear algebra. So, fact. It turns out it's very easy to check if A and B are diagonalizable, simultaneously diagonalizable. So, but for this we need to suppose A and B are diagonalizable, of course. Then, A and B are simultaneously diagonalizable if and only if, and promise you, you might not believe me, but it's too good to be true, but no, it's good and it's true, if and only if they commute. AB equals BA. What? What? I mean, seriously, this is crazy, huh? How can putting, a common basis of eigenvectors be the same as commuting? But it turns out it is true, and let's prove it. The proof is not easy, but it's cool. For First of all, let's do the easy part. If they're simultaneously diagonalizable, then they commute, but that's not too hard. So suppose A is P dP inverse, P dP inverse, and B it's P d prime P inverse, then let's calculate AB, that's P dP inverse, P d prime P inverse. The P inverse, P and P inverse cancel out, and you get P d prime P inverse. But you have to understand, diagonal matrices, they always commute. If we have 2003 times, 4006, that's 2 times 4, 0, 0, 3 times 6, and that's 4 times 2, 0, 0, 6 times 3, and that's 4006, 2003. The general case is similar. So in other words, diagonal matrices, they commute, which means we can just interchange those two. So that's P d prime d P inverse, and then you can just do the reverse. So that's P d prime P inverse P d P inverse, and that's BA. So in other words, commuting is a necessary condition for simultaneously diagonalizable. And now let's show the non-obvious part, that they're, if they commute, then they're simultaneously diagonalizable. Okay. And again, the proof is not easy, and I'm improvising a little bit, so bear with me. So suppose A and D commute. So suppose A and D commute. So suppose AB equals BA. And then show A and D are simultaneously diagonalizable. Alright, so to show something is simultaneously diagonalizable, it's just enough to find P. You want to find P such that, so want to find WTF, P such that P inverse AP is diagonal and P inverse BP is diagonal. Now, remember what it means to be diagonalizable. It's just equivalent to finding a basis of eigenvectors. So what we want to find is a basis of Fn such that we have both eigenvectors of A that are also eigenvectors of B. So goal, find a basis of Fn consisting both of eigenvectors of A and eigenvectors of B. Because suppose you find something like that. So suppose you find a basis beta, which is V1 up to Vn, that are eigenvectors of A and B at the same time, then you can just let P be the matrix whose columns are V1 up to Vn, and you can show it does the job. P inverse AP would be diagonal, and P inverse BP would be diagonal. And I have done a video on that at some other point. Okay, and here comes an interesting thing. So it turns out we need to deal with eigenspaces. So let's assume A has some eigenvalues, lambda 1 up to lambda k. suppose A has distinct eigenvalues lambda 1 up to lambda k. And one thing we know, if A is diagonalizable, then our vector space is just a direct sum of the eigenspaces. So what we know is that Fn is the direct sum of the eigenspaces so somehow what we need to show is kind of vectors, basis vectors, that such that Fn is also the direct sum of maybe eigenvectors of B. And essentially what this decomposition says, it's enough to look at the individual eigenspaces. So now, for each eigenvalue, and again it's for A, right? So it's very important. Eigenvalue of lambda of A, study not the effect of A on E of lambda, but the effect of B on the eigenspace. Of B on E of lambda. So it's kind of interesting. We want to see how B acts on the eigenvectors of A. And here's our first claim. So first important claim is this eigenspace is invariant under the action of B. E lambda is invariant under B. And we'll need this in a second. So why is that true? So in other words, if you start with a vector in E lambda, and you apply B to it, you still get a vector in E lambda. So suppose V is in E lambda, which means, you know, AV equals lambda V, and then show B of V, it's in E lambda. So what would that mean? It means that if you apply A to B of V, you still get, if you apply A to B of V, you get lambda B of V. So maybe to clarify, so let's call this W. Show that if V is in this, W is in this. What this means is you have to check that A of W is lambda of W. But what do we know? AW, by definition, that's ABV. And very important, so far, we have not used the fact that A and B commutes yet. And in fact, this little detail is actually the most crucial part of the proof. Because they commute, we get AB is BA. So ABV is BAV, but we know that AV is lambda V. So we get B lambda V, and putting this lambda out, we get lambda BV, but that's lambda W. So in other words, what's interesting is, if you have an eigenvector of A, and you apply B to it, BV, it's still an eigenvector of A. So that's interesting. So in particular, as I said, this subspace is invariant. And what's nice about invariance is that you can just define a restriction on B on E lambda. So, since E lambda is what's called B invariant, can define a new, matrix or linear transformation called a restriction B restricted to E lambda that goes from E lambda to E lambda, and simply B takes V as its input and spits out, B restricted E of lambda of V, it's simply BV. So in other words, let's say B goes from Fn to Fn. The matrix, and again, I'm abusing notation a bit. I'm using matrices instead of linear transformations. And this is a smaller subspace. Then B restricted to lambda is just the same thing as B. But it just goes from a smaller subspace to a smaller subspace. Alright, that's the first thing. Also, so we know that B is diagonalizable, and here's a beautiful fact. It turns out if you restrict B into any smaller invariant subspace, then the restriction is still diagonalizable. So here's the second claim of the day. And then let's see how we can conclude from that. So if, let's say in general, T from V to V is diagonalizable. I'll state it for linear transformations because it's a bit easier to state in that case. And W, a subspace, is T invariant. Then T restricted to W is also diagonalizable. Alright, and how do you show that? Then, again, my apologies for going into the linear transformation world, but it's the same proof. So, since T is diagonalizable, we know that the vector space, it's a direct sum of the eigenspaces. Okay? And I'm claiming that then W is also the direct sum of some of the eigenspaces. So claim, so maybe, let me give you heuristically the idea. If you take this and you intersect it with W, there's this intersected with W, W is a subspace of V, so the intersection is this. And if you intersect each of them with W, imagine foiling it out, then you get this. E of lambda k intersected W. And in particular, if you can kind of show that those are eigenspaces, so first of all, some of them might be like 0 or something. So imagine you delete all of them or 0, then if you can somehow show that those are eigenspaces corresponding to the restriction, then we would be done. Because then we would get that W, like T restricted to W, is diagonalizable. So yes, let's first show this first claim. So let's first show that E lambda 1 direct sum with E lambda k restricted intersect W. Let's show that this is true. So E lambda 1, this with W, plus that plus E of lambda k restricted to W. And let's do it with what's called set inclusion. So suppose, let's say V, it's in E lambda 1 restricted at the direct sum, E lambda k restricted to W, then V is in W, and V is in E1 lambda 1 direct sum, E lambda k. So V is in W, and V equals to just sum of vectors, W1 plus dot 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 plus Wk, where Wi is in E lambda I. And what you kind of want to show is, I think after deleting vectors of 0, then we get that each of those is in W. So you have a vector W here that's in W, and you get that the sum of those is in W. And what you want to show, so claim, each Wi is actually in W as well. So this is kind of interesting. If you have a vector in W and you write it as a sum of the eigenspaces that are in V, it turns out each of those components is also in W, which is kind of interesting because you have this little picture W, let's say this is V, and you know it's a direct sum of the eigenspaces, so E lambda 1, E lambda 2, E lambda 3, and then let's say E lambda k. The situation is, if somehow you can write your vector V that's in W, but as a sum, as all those components, then it turns out the components are not outside of W, but actually inside of W. And I believe the way you do this is just by induction. So let me show you the inductive steps. So basically induction on K. Because if K equals 1, then there's nothing to prove. Because then what we get, V equals to W1, but we know V is in W, and then therefore W1 is in W. So we're done. And now suppose it's true for K minus 1, and then show true for K. And so assume W, V is W1 up to WK plus K. And then actually the proof is very similar to the fact that eigenvectors corresponding to different eigenvalues are linearly independent. So let's apply T to it. So T of V, that is then T of W1 plus dot 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 plus T of WK. And then T of V, that's then lambda 1 W1 plus dot 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 plus lambda k WK. Because remember, those vectors, they're still in the eigenspaces. So that's why it's still true. Because it's true in V, it's also true in the eigenspaces. T of Wi is lambda I Wi. And then how can we continue? On the other hand, so we know this is in W because W is T invariant. So we know if you start with a vector in W, you get a vector in W. And on the other hand, take this equation and multiply it by lambda k. So what do we know? So we know T of V, it's lambda 1 W1 plus dot 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 plus lambda k WK. And on the other hand, take this equation multiplied by lambda k. So lambda k V equals to lambda k W1 plus dot 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 plus lambda k WK. And then just subtract. So T of V minus lambda k V, that is lambda 1 minus lambda k W1 plus dot 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 plus lambda k minus 1 minus lambda k WK minus 1, and those two, they disappear. Now, what do we know? We know V is in W, T of V is in W, again by T invariance. And so we get this vector in W, which is the sum of vectors in each E of lambda I. But because there are only k minus 1 of those vectors, we get that each vector is in E of lambda I. So it is in Wi. So basically, Wi minus Wk, Wi, it's in E lambda I. Sorry, it's in W. But because those are non-zero numbers, because everything is distinct, we eventually get that Wi is in W. And then coming back to our original equation, V is W1 plus dot 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 plus Wk minus 1 plus Wk. So this is for I from 1 up to k. Minus 1, very important. So the point is we know it's true up to k minus 1. Let's show it's true up to k. So we know each of those is in W. So by subspace, the whole sum is in W. This we said was in W. So Wk is just the difference of two things in W. And that's also in W. So indeed, we have shown that if we have such kind of direct sum, then each of those components is in the direct sum. So indeed, what we have shown is that W intersect the direct sum, intersect E of lambda 1, direct sum, E of lambda k. It's actually just a subset of W intersect E of lambda 1, direct sum, W intersect E of lambda k. And technically, we've only shown the sum part, but I think you can show the direct sum part in entirely similar way. And the other direction is actually easier because suppose V, it's in all those, W intersect E of lambda 1 plus W intersect E of lambda k. Then V is the sum of bunch of vectors, W1 plus dot 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 plus Wk, where Wi is in W intersect E of lambda I. Then in particular, on the one hand, Wi is in E of lambda I, lambda 1 dot 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 E of lambda k. So in particular, V is in the sum of those things. And you can also show it's in the direct sum just by setting this equal to 0, and you get all those vectors are 0 by direct sum. And moreover, we also know Wi is in W. So this thing is in W, this thing is in W. So the whole sum of this is in W. So what we get is V is in W and in the direct sum. E of lambda k. And therefore, it's in their intersection. So the other step is also shown. And therefore, we get equality. All right. So that's good. We get that basically W intersect this equals to this, but again, by assumption, we know that V is a direct sum of the eigenspaces. So V intersect W is this, so W is the direct sum of those things. But we're not quite done, because we would be done if we've shown that W is the direct sum of eigenspaces of the restriction. So claim, and again, it's possible that we're losing eigenvalues. So by this sum, I mean, whenever this is 0, just ignore it, throw it away, and just consider the ones that are non-zero. Because it's not true that you always keep the eigenvalues if you're restricting to any subspace. It's possible that you're losing some. For example, I don't know, keep the this thing, the matrix 1, 0, 0, 2, but just restrict it to the x-axis, then we don't have the eigenvalue 2 anymore. We just have the space with eigenvalue 1. So in this case, the second eigenspace would be trivial, because we don't have the y-axis. All right, and claim, so now W intersect E of lambda I, that is the eigenspace of t restricted to w for lambda I. So if you want E of lambda I prime, where this prime means for the restriction. And well, it's not too hard to show, so suppose V is in W intersect E of lambda I, then what we know is V is in W, and V is in, so T of V equals to lambda IV. But then what about the restriction of this? So T restricted to W of V, well, because V is in W, we get that this is just T of V, and we get that it's lambda IV. So in other words, V is an eigenvector corresponding to T restricted to W. So V is in the second eigenspace. And similarly, if we have V in the first eigenspace, so if V, it's in E of lambda I prime, first of all, it's in W, because we're restricting ourselves to subspace W, and, well, T restricted to W of V, we know it's lambda IV, but because V is in W, this is just the same as T of V. So T of V is lambda IV, so it is indeed the direct sum. And therefore, what we can conclude is that from this, we get W, it's, again, the direct summand of everything, E of lambda 1, restricted, the direct sum, W restricted of E of lambda k, and that's E of W1 prime restricted to direct sum E of lambda k prime. Cool, so indeed our subspace is the direct sum of the eigenspaces for a restriction, and this is by definition the definition of T in restricted W being diagonalizable. So T restricted W is diagonalizable. Alright, now, how can we conclude from this? Because why did I do this gibberish? What do we have so far? We found, so far, going back to our matrix A, we know that Fn, it's the direct sum of E of lambda k, where the E of lambda I is the eigenspace of A. Of A for lambda I. Right? On the other hand, we know on each lambda I, E of lambda I, again, the subspace corresponding to A is B invariant. So, B restricted to E of lambda I now is diagonalizable. Which means we can find a basis of E of lambda I corresponding to eigenvectors of B. So for each B, so for each I, we can find a basis. Let's say Vi1, Vi lambda I, or I guess Mi or something, of E lambda I corresponding to eigenvectors of B. Of B. And just careful, I don't think necessarily with the same eigenvalues. So you have to be slightly careful. Alright, but that's good. Still, we can solve it. And by the way, not the same eigenvalues, because at the end, the diagonal matrix isn't the same diagonal matrix as in A. But that's still actually enough to conclude, because one of the conditions of direct sum is simply if you have one basis of one space and bunch of other ones, then if you take the union of the bases, you get a basis for Fn. So beta 1 is this, a basis of eigenvectors of B, and then you can actually show that beta equals to a union is a basis of Fn corresponding to eigenvectors of B. And the cool thing is, this has nothing to do with eigenvectors of A a priori. So this fact, we can just put bases together and you get a new basis. That just corresponds to the direct sum property. And there's another video I've done on direct sums of eigenvectors where I basically prove that as well. So you feel free to watch that. And therefore, what can we show? We get a basis of Fn corresponding to eigenvectors of B. And therefore, first of all, B is diagonalizable, but we know that. But the point is, this will be the common basis. You see? Because with beta, so I claim this beta works. And why is that? Because on the one hand, if you just put all those eigenvectors together, that's how you can form your matrix P. P is, V1, 1, V1, M1, and then V2, 1, V2, M2, VK1, VK, MK. And with this matrix, you get that P inverse BP is diagonal. But here's the important thing. Those vectors, they're not arbitrary. They're also eigenvectors of A, because we defined E of lambda I to be the eigenspace of A. So if you apply A to those vectors, you still get that they're eigenvectors. And because Fn, I guess we can say that the sum of the mk's is n. So because Fn is n-dimensional, we also get a basis, like with the same basis, we also get a basis of eigenvectors of A. But since beta is also a basis of eigenvectors of A, with the same P, that's the important thing. We get P inverse AP is diagonal. You see, because we started with the eigenvectors of A, and we just modified the same set to get eigenvectors of B. So in some sense, with the same P, we can get also the same diagonal matrix, which also gives you kind of, not quite, but some idea of how to find P. Because first of all, find all the eigenspaces of A, and then for each eigenspace, see how you can tweak it to get eigenspace of B. And then with this clever choice, you go back and you find that it also works for A. And therefore, we simultaneously diagonalize the two matrices. And notice the subtle nature of how we use commutativity, because we just use it to say that something is T invariant. And once we saw it's T invariant, then in fact, we're able to find, that's diagonalizable and get like nice spaces out of it. All right, I hope you like this, well, I want to say little but pretty long video. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.